The exponential distribution. A continuous random variable, x, is said to have an exponential distribution if its probability density function is of the form f of x equals lambda times e to the minus lambda x for x positive. Here, lambda is a positive number, a real parameter value for the distribution. The density function is 0 for negative values for x, but decreases exponentially from 0 on to the right for positive values. An exponential plot for the density function is given here. An exponential distribution is often used to model a time. For example, the time until some event occurs. It may be the time that you need to wait for the next bus to arrive at a stop. The length of time until there is an accident at a given intersection. The time until a major claim at an insurance company. And in general, for a Poisson process, which is used to model events occurring over time, the length of time we need to wait for the occurrence of the first event. In this case, that random time has an exponential distribution. As another example, the length of time between phone calls to an emergency 911 line would typically be approximated with an exponential distribution. The exponential distribution cumulative distribution function. If x has an exponential distribution as given by the previous density, then its cumulative distribution function is capital F of x equals 1 minus e to the minus lambda x for positive values of x, and f of x equals 0 if x is negative. To prove this, note that for positive values of x, the cumulative distribution function is the integral up to x of the density function. In this case, the integral from 0 up to x of f of z dz. And if I substitute the value of the density we saw earlier, lambda e to the minus lambda z, and change variables so that lambda z is replaced by w, then we end up with an integral from 0 up to lambda x of e to the minus w dw. This integrates to 1 minus e to the minus lambda x. So the cumulative distribution function, 1 minus e to the minus lambda x. The exponential distribution is often used to model the time between events for a Poisson process. Suppose x is the time to the first event in a Poisson process. F of x is the probability that x is less than or equal to little x, is the probability that the time to the first event is less than or equal to x. Of course, we can rewrite that as 1 minus the probability that the time to the first event is bigger than x, which, stated another way, is 1 minus the probability that there are no events at all in the interval from 0 up to x. So in this graph, I've plotted the interval from 0 up to x in red. We'd like to know the probability of no events over this period of time. For a Poisson process, the number of events in that interval has a Poisson distribution, and the expected value of that number is lambda times x, the length of the interval. So the probability of no events in this interval is lambda x to the power 0, e to the minus lambda x over 0 factorial. 1 minus the probability of no events turns out to be 1 minus e to the minus lambda x. And this turns out to be the cumulative distribution function of an exponential random variable. What we've shown is that the time to the first event in a Poisson process has an exponential distribution with parameter lambda. It's not hard to show that that's also true of the time between the first event and the second events in a Poisson process. The exponential distribution describes the time between any consecutive pairs of events in a Poisson process. Alternate parametrizations of the exponential distribution. It's fairly common to use a different way of parametrizing the exponential distribution. Suppose I use the expected value to parametrize it. I set theta equals 1 over lambda as the parameter. Then when I rewrite the exponential distribution, the cumulative distribution function now becomes 1 minus e to the minus x over theta, and the probability density function 1 over theta e to the minus x over theta. This is exactly the same density and cumulative distribution function. The only difference is the parameter that we've used, the gamma function. There's a very useful special function, useful in most calculations involving the exponential distribution, called the gamma function. It's a function that needs to be defined through an integral. Suppose alpha is some positive number. Then we define gamma of alpha to be the integral from 0 to infinity of x to the power alpha minus 1 e to the minus x dx. This is called the gamma function, and it's defined, at least here, only for positive values of alpha. You'll see a partial graph of it here. The graph doesn't go very far to the right, nor is it accurate near 0, because in both cases it approaches infinity. The gamma function has an interesting property, a recursive property. For example, if you know gamma of 1 or gamma of 2, you can calculate gamma of 3, gamma of 4, and so on. In general, for any value of alpha, gamma of alpha is alpha minus 1 times gamma of alpha minus 1. It turns out that gamma of 1 and gamma of 2 are both equal to 1. Gamma of 1/2 is the square root of pi, so it's going up from 1 now. Gamma of 3 is 2, gamma of 4 is 6. As we mentioned earlier, it goes up to the left and it goes up to the right. And the gamma function is really a continuous modification of the factorial. If alpha is a positive integer, then gamma of alpha is alpha minus 1 factorial. Let's prove this. At least we'll start by proving that gamma of alpha is alpha minus 1 times gamma of alpha minus 1. This is really just an exercise in integration by parts. For any value of alpha bigger than 1, we can write the integral from 0 to infinity, x to the alpha minus 1 e to the minus x, by integration by parts, as minus x to the alpha minus 1 e to the minus x, evaluated from 0 to infinity, plus alpha minus 1, the integral from 0 to infinity x to the alpha minus 2 e to the minus x dx. You'll notice that the second term here involves the gamma function corresponding to alpha minus 1. So this equation becomes alpha minus 1 times gamma of alpha minus 1. The first term evaluates, as it turns out, to 0. Now it's easy to check that gamma of 1 is the integral of x to the power 0 e to the minus x, and that's 1. And that determines all the subsequent values of gamma of alpha for integral alpha. Putting alpha equals 2, we get gamma of 2 is 1 times gamma of 1, which is 1. Gamma of 3, 2 times gamma of 2, which is 2. Gamma of 4, 3 times gamma of 3, which is 3 times 2, or 3 factorial. The other value of gamma we mentioned above, gamma of 1/2 equals the square root of pi, can be proved using double integrals. We won't go into that here. Now let's calculate the moments of the exponential distribution. Suppose x has an exponential distribution with parameter lambda. Then the expected value of x is 1 over lambda, and the variance of x is 1 over lambda squared, the square of its expected value. It's easy to check the expected value. It's the integral of x times f of x dx from 0 to infinity, which is the integral of x lambda e to the minus lambda x dx. And if you change variables to z equals lambda x, this becomes 1 over lambda times gamma of 2. And remember, gamma of 2 is 1, so that's 1 over lambda times 1, or 1 over lambda. To continue the proof, let's determine the expected value of x squared, the integral of x squared f of x dx. By almost exactly the same routine as before, this is the integral of x squared lambda e to the minus lambda x dx from 0 to infinity. Again, on changing variables to z equals lambda x, this becomes 1 over lambda squared times gamma of 3, or 2 factorial times 1 over lambda squared. And since the variance of x is e of x squared minus the mean expected value of x, the quantity squared, this becomes 2 over lambda squared minus 1 over lambda squared, or 1 over lambda squared, verifying the form of the variance. Here's an example. Suppose calls on a hotline arrive according to a Poisson process, and there's an average of 4 calls per hour. So the intensity of calls, lambda, is 4 per hour. Find the probability, first, A, that you have to wait more than 15 minutes for the first call. And second, if after 15 minutes no call has been received, that you'll have to wait another 15 minutes longer for that call. Solution. Let x be the time of the first call, and we'll express time here in hours. Then x has an exponential distribution with lambda equals 4. What's the probability that x is bigger than 1/4 of an hour, 15 minutes? Probability x is greater than 1/4 is 1 minus the probability that x is less than or equal to 1/4, or 1 minus the cumulative distribution function of x evaluated at 1/4. Remember the form of the CDF of an exponential distribution. F of x is 1 minus e to the minus lambda times x. So if in place of lambda we put 4 and in place of x we put 1/4, then the probability x is bigger than 1/4 is 1 minus the quantity, 1 minus e to the minus 4 times 1/4, which is e to the minus 1, or 0.368. You might think that if the average time to the first call is 1/4 of an hour, then the probability that the first call occurs after 1/4 of an hour should be about half. It's not. According to this calculation, it's about 36.8%. The second part of the question asks the following. If x is the total waiting time, and if you're told that x is bigger than 1/4, what's the probability, given that x is greater than 1/2? And if we simply use the definition of conditional probability, this is the probability x is bigger than 1/2 and bigger than 1/4, divided by the probability x is bigger than 1/4. Well, of course, the numerator, the probability x is bigger than 1/2 and bigger than 1/4, is just the probability x is bigger than 1/2. And now both the numerator and denominator can be evaluated using the cumulative distribution function for the exponential. This becomes, in the numerator, 1 minus 1 minus e to the minus 4 times 1/2, and in the denominator, 1 minus e to the minus 4 times 1/4. E to the minus 2 over e to the minus 1, which turns out to be exactly the same number as we obtained earlier, 0.368. This is quite curious. The probability we have to wait 15 minutes is 0.368. But if we've already waited 15 minutes, the probability we have to wait another 15 minutes is exactly the same, 0.368. This is referred to as the memoryless property of the exponential distribution. For a Poisson process, whether or not you've already waited 1/4 of an hour for an event doesn't influence how long you still have to wait for an event. In terms of the distribution of waiting times, this is referred to as the memoryless property of the exponential distribution. If you've already waited b units of time, in other words, if you're given that x is bigger than b, the probability you have to wait an additional a units of time, the probability x is bigger than a plus b, given x is bigger than b, is identical to the probability that x is bigger than a. If buses arrive according to a Poisson process, there's no point in stationing someone near the bus stop to inform you whether or not a bus has gone by in the last 10 minutes. The expected value and the distribution of the time you will have to wait when you arrive at the stop is identical with or without this information.